Next up, we have Miquel from the University of Southampton and one of the 2025 CoSeC Fellows, who's going to talk to us about modelling subgrid turbulence in simulations.
Hi, everyone, again. Well, thank you for the introduction. Yeah, the talk today is going to be about how to model subgrid turbulence in the context of neutron stars. Let me start with what a neutron star is. Neutron stars are amongst the most compact objects in the universe. They are usually born during the collapse of the core of a massive star, and the matter is subject to extreme conditions. For example, the densities in the core of these stars reach the nuclear densities up to 10 to the 14 Gauss per centimeter cubic. They also possess the most intense magnetic fields in the universe. Magnetars, for example, reach magnetic field strengths of 10 to the 16 Gauss. They also have very high rotation velocities with angular frequencies of the order of kilohertz. And as you can see, these conditions cannot be reproduced in terrestrial laboratories. So in order to study these objects, in order to study the matter extreme conditions, we need electromagnetic and also gravitational wave observations that might provide more knowledge in the neutron star physics. And also, in order to understand these observations, we need realistic enough numerical simulations of these objects. So neutron stars can also be found in binary systems. So after a long-lasting spiral phase, they eventually merge. And the product of the merger will depend on the total mass of the system and of the equation of the state of the matter, but usually consists of a black hole surrounded by an accretion disk. Sometimes there can exist a short-lived phase where a hypermassive neutron star is formed. And during this post-merger phase, where the hypermassive neutron star hasn't collapsed yet, a large amount of physical processes take place. So for example, here we have the two neutron stars, they merge, and we have different possibilities depending on the total mass of the system. So if the system is very massive, it will promptly collapse to a black hole, as you can see here. Otherwise, it will be a hypermassive neutron star, and then again, might collapse to a black hole, or if the mass is not too large, it will end up being a supramassive neutron star, which will be stable against collapse. So in this scenario, in BNS mergers, there can exist transfer of energy across a large range of spatial scales, known as the inertial range of scales, and turbulence can be quantified by the Reynolds number, which is the ratio between the inertial forces over the viscous forces. So in BNS mergers, for example, the Reynolds number can reach values up to 10 to the 15 or 10 to the 16. And for information, a fluid is considered regarded as turbulent when the Reynolds number is 10 to the 3. So you can see the fluids in BNS mergers are very, very, very turbulent. So in this figure here, we can see that before merger, the energy is stored in quite large scales of the order of kilometers, but then when merger occurs and also after merger, both the kinetic and also magnetic energies are transferred to smaller scales due to a direct cascade of turbulence. And you can see that there's energy developed at the scales of the order of centimeters. And you will see later that this is very difficult to resolve in numerical simulations. So magnetohydrodynamical or MHD turbulence can lead to angular momentum transport in the merger remnant, which can have an impact on the black hole formation time and also on the mass ejection rate, which can affect the nucleosynthesis of heavy elements. And also can lead to magnetic field amplification, which can have an impact on the formation of an ultra-relativistic jet after the merger. So there are several processes or instabilities that generate MHD turbulence, such as the Kelvin-Helmholtz instability, which occurs during the merger of the neutron stars when the interfaces touch. And this leads to an amplification of the small-scale magnetic field. And we also have, after merger, the magnetorotational instability, or MRI, and magnetic winding, which amplify the large-scale magnetic field. So direct numerical simulations of BNS mergers become too computationally expensive when dealing with MHD turbulence. These simulations also need to account for neutrino treatment, also a realistic equation of state. So we need a very high spatial resolution to properly capture the small scale physics. As an example here, we have the molecular dissipation scale in this simulation is of the 2 centimeters, or the wavelength of the fastest growing mode of the MRI is of the order of meters. So we need to reach resolution of these scales in order to capture the proper physics. As an example here, we have a pretty, well, not that recent simulation, but it's one of the most with the highest resolution up to date. So here you can see this is the magnetic field strength. You can see how the magnetic field is evolving just after merger, and you can see that with a final resolution of 37.5 meters, which is quite a lot for this kind of simulations, the magnetic field strength reaches 10 to the 15 Gauss more or less. But when using 17.5 meters, which is a crazy high resolution, we can see that there's no convergence and we reach an amplitude of 10 to the 16 Gauss. So even with a super prohibitive large resolution, we cannot find a convergence value of the magnetic field amplification. So there's a possibility there are several possibilities to solve this issue. The first of all is to improve the numerical methods. We can use higher order schemes in finite difference, finite volume, and also finite elements. We can also improve or increase the resolution, but we need the exascale infrastructure and also efficient adaptive maze refinement and also the use of GPUs, and this is a bit difficult. And the last, which is the one I'm going to focus on, is the use of large eddy simulations. So what is this? So these large eddy simulations aim to describe the small scale physics with subgrid models. So these simulations employ modest resolution, and these models describe the dynamics at smaller scales than the computational grid. And they are widely used in aerodynamics and also meteorology. Here we have a picture of how they work. So when we have a direct numerical simulation, we are able to capture or to resolve all the scales in the problem, from the large scale eddies to the dissipating eddies. But when we have a simulation that is not able to capture the whole inertial range of scales, we will resolve part of the range, but the smaller scales will be modeled by our subgrid model. So what we can do now is to separate our fields, magnetic velocity fields in our simulation, between resolved and unresolved scales. So here we have a slowly varying background plus a rapidly fluctuating residual, which represents the turbulent contribution to the field. So if we apply this decomposition to the ideal MHD equations, where when we neglect gravity and nuclear reactions, we have zero source terms, we will find that products of turbulent components will arise new terms in this equation. So we will end up with effective source terms that we will have an impact in the simulations. So these turbulent contributions can be written in this way if we only consider perturbations in the magnetic and velocity fields. So we have the Maxwell stress, the Reynolds, and the Faraday stress tensor. And the aim of these subgrid models is to find a closure for these turbulent stress tensors. So here we have an example. We have here the Burger's equation. So if we apply this filtering operation and we decompose the fields into this slowly varying part and the turbulent contribution, we can see that when we filter this term, we will have an additional contribution due to the small scales. Okay, you can see here we have the average of the square of the perturbation. So this new subfilter scale tensor is unknown because it belongs to the smaller scales, smaller than the computational grid, and we have to model it. So there are several models I will show you later. For example, we have this Mauryski model, where we can represent this contribution as a derivative of the resolved field, and also, for example, the gradient model, where again we use some derivatives in order to model the turbulent contribution. So here there are some examples of applications of subgrid models to actual BNS simulations. For example, here from 2015, these people came with an additional term for the induction equation for the vector potential. So, well, you can see that they come up with this term, which is made of several several coefficients that have been obtained from phenomenological arguments, I believe. So you can see here, this is the most important plot, I believe. So when you don't use any subgrid contribution, you can see the magnetic field is not amplified due to a lack of resolution in the simulation. But when you add this additional effective term, you obtain the expected exponential magnetic field amplification when the merger occurs. Here there's another model. In this case, these grid contributions or these effective terms are not applied to the induction equation. They are applied to the momentum and energy equations through this term here. And you can see that the authors use this turbulent viscosity, which is modeled by this constant here, and this needs to be calibrated. So, for example, here they use several values for this mixed length scale, they call it, and you can see that depending on the value you use of this constant, you will get the collapse to a black hole at a different time. And also it can have an impact on the gravitational wave emission. You can see here the gravitational wave spectrum, how it can change when you change also the constant for this subgrid model. And last but not least, we have the so-called gradient model. This has been applied in several works already, and again, it adds an additional contribution to the induction equation for the magnetic field, making use of gradients of the conserved variables. So, well, I will skip all the details, but so they only, at the end of the day, they only modify this equation, which is the equation for the magnetic field evolution, with this additional term here. If you want to check, the paper is here, but this is a really long expression. But basically, they end up with this result, as you can see here, when they apply a large eddy simulation with a medium resolution, they reach the same amplitude as when they use a simulation with a much higher resolution. So they find this convergence when applying the large eddy simulation, as you can see here, for the magnetic field amplification during merger. So now I want to talk about a model I developed together with collaborators back in Spain, in Valencia. So we came up with a model which is based on the evolution of the turbulent kinetic energy density. So what we did is to define a partial differential hyperbolic evolution equation for this energy density, which tracks the development of turbulence in neutron stars. And the source terms of this equation will depend on the stability that we are dealing with. As I said before, in neutron star mergers, we can have the Kelvin-Hale stability. We can also have the magnetorotational instability. And our ansatz is that the turbulent stress tensors, which are the quantities that appear in the MHD equations, will be proportional to this turbulent kinetic energy density. Sorry. So I'm going to focus here only on the magnetorotational instability, which is an instability of differentially rotating magnetized fluids, and it leads to transport of angular momentum and also to the amplification of the large scale magnetic field. So in order to have the instability, we need a differentially rotating fluid, and the rotation frequency has to decrease radially outwards. The growth rate of instability is proportional to the rotation frequency of the fluid, and it leads to the formation of axisymmetric modes which have this size. As you can see, it's of the order of hundreds or also tens of meters. So here we have a short movie. You can see here the axisymmetric channel modes that are formed, and you can see that at some point they are disrupted, and we end up with a turbulent state here, as you can see here. And what's going on here? Why does this happen? Why do we have this disruption of the channel modes? So these nonlinear MRI modes are unstable to the so-called parasitic instabilities, which are secondary instabilities that feed off the main instability, the MRI. So here we have, in log scale, we have the exponential amplification of the MRI, and these secondary modes grow super exponentially until they reach more or less the same amplitude as the MRI, and will lead to a saturated state of sustained turbulence. And here we have a confirmation of this through numerical simulations. You can see here the exponential growth of the MRI and the super exponential growth of the parasitic instabilities. So in order to come up with an evolution equation for this turbulent kinetic energy density, we actually need two equations. One for the main instability, the MRI, but also another one for the secondary instability, the parasitic instability, which is the responsible for the saturation of the MRI. So here we have several expressions for the different terms. This is the growth rate of the main instability. This is the growth rate of the parasitic instability, which acts as a sinc term for the equation for the MRI. You can see that it's proportional to the amplitude of the MRI energy. And here we have this sinc term, which represents the dissipation of energy at the end of the inertial range of scales. So as I said before, now what we want to do is to relate this quantity to the turbulent stress tensors that show up in the MHD equation. So what we do is to apply these proportionality coefficients to the energy densities in order to obtain the turbulent stress tensor. So we found that the MRI coefficients here, these ones here, are known from analytical studies. So perfect, we don't need to worry about them. But the parasitic coefficients need to be calibrated with local box simulations, and that's what we did. So our late work here, which is very, very recent, it's in the archives. It has been in the archive just for a couple of months. We performed axisymmetric two-dimensional global simulations of a differential rotating magnetized neutron star with this code, the INUS code, and we just employ a purely toroidal magnetic field confined inside the star. And what we did is to modify the momentum equation with these additional subgrid contributions, the stress tensors. And in this case, the earthy component leads to the angular momentum transport that we expect due to the turbulence from the MRI. So here we have some plots. These are the turbulent kinetic energy densities that I told you about. The solid line is the MRI energy, and the dashed line is the parasitic energy, which you can see that grows super exponentially. And for different rotation frequencies, since the growth rate of the MRI is proportional to the rotation frequency, it will grow faster for larger values of omega. And also, there's a dependence on the magnetic field strength. And for a larger magnetic field strength, we end up with larger values of the turbulent kinetic energy density, which translates to a larger or a higher or stronger, let's say, angular momentum transport at the end of the day. So here we have some radial profiles. So these are the most important results. You can see here that the dashed line are simulations. It's a simulation that doesn't employ the subgrid model, and you can see here that there's some numerical dissipation, and you can see that there's a bit of decrease on the profile of the angular rotation. But when the subgrid model is applied, we end up with a plateau of uniform rotation, which is what we expect when angular momentum transport is occurring. And you can see that the degree of angular momentum transport is much higher compared to this numerical dissipation. And here we have this shear parameter known as Q, which tells us the degree of differential rotation that we have in the system. And for a Q equal to 0, it means that we have 0 differential rotation, so uniform rotation. As you can see here, that as time goes by, we are reaching values of 0, which for regions from inside the core and towards larger values of the radius. So you can see here that angular momentum transport is occurring, and the angular momentum is being transported outwards as time goes by. So to conclude, we have seen that subgrid models are an alternative to the use of prohibitive large resolution and also expensive numerical methods in numerical simulations of hydrodynamical turbulence. And large eddy simulations are currently being performed in the context of neutron star mergers. We have some promising results. So the minute model is able to reproduce the turbulent angular momentum transport due to the MRI. And also other large eddy simulations are able to reproduce or capture the magnetic field amplification during merger due to the Kernighegel stability. And regarding future steps, so we want to extend the model to also study the MRI dynamos, or the large-scale magnetic field amplification due to the MRI. And we want to export the model to other astrophysical scenarios, such as core collapse supernovae and accretion disks around supermassive black holes. And of course, we aim to also apply AI and machine learning techniques to model turbulence in this kind of simulations. So that's everything. Thank you very much.
Brilliant. Thank you very much for that interesting talk. I think we've got time for a quick question.
Yeah, it's for the subgrid model for application in engineering flow, it's easy to validate whether it's good or not. For your case, how to validate your new model is capture the real physics because you got some analytical coefficient there and some.
It's a really good question. The problem here is that what we normally do is to perform local box simulations in which we have enough resolution to solve the instability we want to study. So we can calibrate the coefficients of the model there and also like validate our results. But when we transition to global simulations, we have to do a leap of faith, let's say, because it's difficult to know if the results from local box simulations also apply for global simulations. But it's the only thing we can do. So we just perform local box simulations where we can capture instability and then believe that this applies also to global scenarios.
Brilliant. Let's thank Miquel one more time.